Welcome back. In this video, we are going to learn about the elastic strain energy that the axially loaded member can store when subjected to an axial, that is tensile or compressive load. Using this question as a reference, which is from GATE-ME 2013, and then try to answer it. So let's first read out this question and analyze it. Right. For what is given and what is asked. Two threaded bolts A and B of same material. Right. So first information that we have been given here is that both bolts are made of the same material, meaning they have the same material property such as the same elastic modulus. Right. Now let's move on. And length. So both bolts A and B are of same material and length. So both bolts also have same lengths. LA equal to LB. Now we move on further. Are subjected to identical tensile load. So both bolts are also subjected to the identical tensile load. Right. So let's move on further. If the elastic strain energy stored in bolt A is 4 times that of bolt B. So this information is also given that elastic strain energy stored in bolt A is 4 times that of bolt B. Right. And further, the mean diameter of bolt A is 12 mm. Right. So that's the given information. And the question asks about the mean diameter of bolt B in MMs. So this is the given information that we have. Now, and diameter of bolt B is to be determined. Right. So basically, what this question is asking is about the mean diameter of bolt B. All right. And what we have been given here is a comparison, right, between the elastic strain energies of 2 volts. Hence, what we need here is an expression or formula of the elastic strain energy associated with an axially loaded member, which in this scenario is a threaded bolt. Now, we can just recall that formula, then this question can be easily solved. However, if we can't recall it, then we would just have to derive it using our basic knowledge and then solve this question. Now, before we move on, let's assume that the each threaded bolt is an equivalent to an axially loaded bar or member of length L, diameter D, and elastic modulus E, and subjected to force F. And draw the diagram of the bar. So we have the axially loaded bar, which represents the axially loaded threaded bolt. Now, let's write an expression of the elastic strain energy stored in a axially loaded bar. So we have the expression of the elastic strain energy due to axial load, where A is the cross section of the bar, which is circular of diameter d. So let's plug in the expression of A, which is equal to pi by 4 times diameter square. So after plugging in the expression of A into this, we get this, right? A is replaced by pi by 4 times d square. Now, if we can just look at this expression, we see here that F is same for both the bolts because both bolts are subject to the same axial load. Now L is same for both the bolts because both bolts are of the same length, and E is also same for both the bolts because both are made of the same material, and 2 and pi by 4 are also constant. So this expression becomes U is proportional to inverse of d square. All right. All right, we got this. Now we can also write this expression as u times t square equal to constant. Now we can write this for both the bolts because u times t square is equal to constant. All right, so we can say that this quantity u times t square would be same for both the bolts because it's a constant. So there we have it, this relation. Now by rearranging it, we can find the expression of dB because its value we need to determine. So after rearranging this, we get dB square is equal to this expression. Now applying the square root on both the sides, we get the expression of dB is equal to this. Now we would plug the value of dA and the a value of UA, which is equal to 4 times UB. So we have it. Now we would simplify it. There we have it. The value of dB is equal to 12 times square root 4. We would further simplify it. So there we have it. The value of dB after simplifying the calculation is equal to 24 mm. Correct answer is option B. In case, let's suppose if B cannot recall this expression of elastic strain energy due to the axial load stored in the bar. So what we will do is to derive this using basic formulas and our basic knowledge. Right. So to begin with, as we can see that each threaded bolt is an elastic member. Right. So the corresponding assumption that the bar is an elastic body. Right. So we know that when an elastic body subjected to an axial force such as this F, it stores elastic energy, right? So this axial loading of the bar becomes analogous to an axially loaded spring, right? Because spring stores energy when subjected to a force in the axial direction, because spring is an elastic body. So our bar or a threaded bolt is also a elastic body. So we can use the same formula of the elastic strain energy that we use for the spring. So we have the formula for the elastic strain energy stored in a spring of spring constant K, and the increase in the length of the spring is X. So we can use this formula for our case here, because this bar is also behaves like a spring which is loaded with the axial force, right? Because our bar, which is actually the, from our assumption, is a threaded bolt, right? So this bar is a elastic material just like the spring and subjected to force F. Alright, so there we have it, an equivalent spring. Alright, so we replaced the bar with an equivalent spring which is also subject to the force F. Alright, and with elastic constant K. And for this spring, the stored elastic energy is given by this half K x square, where x is the extension of this spring. So this basic formula is we never forget. So we would begin from this formula. Now, since we do not know the value or the expression of K and X corresponding to the axially loaded bar, so we would try to eliminate it, right, using the formula of F in terms of extension of a spring and spring constant. So there we have it. F is equal to K into X, right? So we would use this formula, all right, to replace Kx with F, and the resultant formula becomes as this. So we replaced Kx with F in this expression, and we got U is equal to half Fx. Now we need to eliminate X, alright, because we need this elastic strain energy formula in terms of force, length, cross-sectional area, and elastic modulus. So we need to eliminate X, alright. So to eliminate X, we would look at the bar, and we can find its extension X, right, using the formula of the linear strain, alright. So the strain energy becomes equal to half F times linear strain times L, right? Because we know the linear strain is equal to the ratio of change in the length, which is X, divided by initial length, alright? So this linear strain is the linear strain of the bar, right? So we replaced X with epsilon L. Now we further have to eliminate this epsilon, which represents the linear strain. So for this we would use the stress strain relation for the axially loaded bar, right, from Hooke's law, because Hooke's law is applied for the elastic material. So for the linearly elastic material such as this bar, the stress that induces in it due to the applied force F is proportional to strain, right? So we would use that expression of stress sigma is equal to E times epsilon, where E is the elastic modulus, to eliminate this epsilon. So there we have it. U is equal to half F sigma upon E times L. So we replaced epsilon with sigma divided by E, because from Hooke's law for the elastic material, stress sigma is proportional to linear strain, right? Where E is the constant, which is elastic modulus. So we replaced epsilon with sigma divided by E. Here we further have to eliminate sigma, and for this we would use the formula of the axial stress in terms of, so using the stress formula, which is equal to applied force divided by the cross-sectional area A, alright, and we eliminated sigma from this expression and replaced sigma with F divided by A, and after simplifying, this expression becomes as this: F square L divided by 2AE, which is the same as this expression, alright. So if we forget this elastic strain energy relation due to axial load, we can just derive this expression